Good evening, everybody, and welcome to this year's Moossa J. Arman Colloquium, Science and Innovation in Physics. My name is Miquel Garcia Garibay. I am the Senior Dean of the College and also the Dean of the Division of Physical Sciences. So, as a Senior Dean of the College, I get to interact with people across the college. But in my role of Dean of Physical Sciences, I get to interact with the people that I'm intellectually most close to, the Physical Sciences Department. And of course, Physics and Astronomy is one of them, one of our best departments, one of our most decorated and prestigious departments. But in addition to Physics and Astronomy, the Division of Physical Sciences includes the departments of Atmospheric and Oceanic Sciences, Chemistry and Biochemistry, Earth, Planetary and Space Sciences, Mathematics, and Statistics and Data Science. We also host the Institute of the Environment and Sustainability. And as you went through the list, you notice that many of these departments, well, one could argue that all of these departments are practitioners of physics in one way or another, right? We can reduce the physical sciences into different aspects of physics and how we look at the world. I'm an organic chemist, so I look at pictures of molecules and think about how they may react and what properties they might have. So the department is, of course, a home to amazing scientists in many disciplines, including theoretical physics, quantum computing, astrophysics, and we host one of the strongest plasma groups in the country, and plasma is, of course, a topic. Plasma and fusion is a topic that I know many in this audience are very passionate about. In fact, the topic of today's lecture is nuclear fusion, which is probably the most exciting among all of energy generation technologies, and one that could, in principle, be truly clean. And we know that there's some revolutionary advances over the last couple of years. So to learn more about that, we are delighted to welcome a prominent expert in this field, Dr. Stephen Cowley, as this year's Moossa J. Arman Physics Colloquium speaker. Now, before I turn it over to Professor Troy Carter to introduce our speaker, I would like to share a bit of insight into the Arman Colloquium. The Arman Colloquium series was created by a generous gift to the Department of Physics and Astronomy by the family of Moossa Arman, a distinguished alumnus of our PhD program in physics, and an eminent physicist and inventor who is known for advancing the frontiers of elementary particle physics and experimental nuclear physics. As the subtitle of this lecture series, Science and Innovation, suggests, Moossa Arman spent his life advancing the frontiers of physics in academia and industry through his groundbreaking research. We are very appreciative of this colloquium series and are proud to know that today's talk would have been of particular interest to Moossa. We value the opportunity to invite members and friends of the department to hear and exchange ideas with experts from other institutions, such as Dr. Cowley. Lectures like this and so many other critically important aspects of what we do would not be possible without philanthropic support. So we thank the Arman family, including Diana and Dean, who are here with us today. So thank you so much for your support. We're delighted that every one of these lectures, we are joined by someone from the family, which also means, not only the trust that they have in the science that that Moossa did in our department, but that our department is really one of the really best that one can think of at UCLA. Clearly, your support is very important to us and is very much appreciated. So with that, I think it only remains for me to ask Troy Carter, Director of the UCLA Plasma Science and Technology Institute and Director of the Basic Plasma Science Facility at UCLA, and professor of the Department of Physics and Astronomy, to introduce our speaker. Please, Troy.
Welcome, everyone. It gives me great pleasure to introduce a good friend and colleague and a friend of UCLA, Dr. Steve Cowley, who's the director of the Princeton Plasma Physics Laboratory. I should have started by saying it serves Steve Cowley because Queen Elizabeth did the thing with the sword to Steve for things that I'll talk about in a second. But Steve went to his undergraduate at Oxford University, Corpus Christi College, which becomes part of the story later. Went to Princeton as a graduate student studying plasma physics and fusion at that point in his career. Spent time as a postdoc at Colloquium, which is the UK lab for fusion, which he came back to later, as I'll say. Back to Princeton for a while as a staff member there, but then came to UCLA. So in '93, Steve joined the faculty at UCLA, was here through 2008, so we overlapped for about 8 years, I guess, while he was here. Rose to the ranks to full professor, and then was called away for bigger tasks. He did spend some time at Imperial College in London during that stint, but then went over to take over the directorship or the lead of the UK fusion program for several years, was running the Colloquium lab, helped do many things there, including extend the run of the jet tokamak, which many of you may have heard, broke a record in fusion power production recently, fusion energy production, 69 megajoules, and also helped get the mass upgrade device going, which many of our staff at UCLA work on right now. Steve spent some time after that at Corpus Christi as the president, so going back to his original undergraduate institution, and led that for a couple of years, one of the first scientists to do so, I think. And then the opportunity to lead one of the most important labs in the fusion program in the US at Princeton opened up, and Steve has been there since 2018, I think. And we're very happy to have him. The list of honors that Steve has is long. Many fellowships, fellow APS, Royal Society, Royal Academy of Engineering, and of course, he's a Knight Bachelor, which means I think the students that work with him are called squires now, so that's good. Anyway, so we're very glad to have Steve. Please join me in welcoming him to give his talk. Yep.
Troy and I were in the emergency room at 1:30 in the morning this morning. You can have no greater friend. Thank you very much. I want to thank the family of Dr. Arman for this lecture series, which I think is important for the department. Dr. Arman actually did work in plasma physics and in microwave devices. He worked for the Air Force research labs, and I think maybe would have appreciated a talk about where we are in plasma physics and where we are in fusion. Walking across campus, had many unbelievably happy years here at Princeton, and it was a bit like coming home. And my kids went to the elementary school on campus, and we were very happy here. And so it's delightful to see old friends and to be back here in UCLA. My story starts in the late 19th century. And in the late 19th century, the theory of what the sun was quite simple in some ways and profoundly wrong. Due to a suggestion from Helmholtz, Lord Kelvin had calculated the age of the sun. And he did it like this. He said the sun is a great ball of gas, and it's collapsing in on itself, and as it collapses in on itself due to gravity, it heats up. As it heats up, it gets pressure, and that pressure pushes back against gravity, and that supports the sun. That bit's true. But as it radiates away that energy, it gets cooler, and then it shrinks a little further. And more gravitational energy is released as it shrinks a little further. It gets a little hotter, and it radiates some more, and it shrinks a little further, and it radiates some more. And this theory of the origin of the sun persisted for about 40 years. At the end of the 19th century, actually, it's more like 60 years. I can't count. It's a problem for a theoretical physicist. Hey, experimentalists do it much better. Yeah, I knew you would agree. This was a real problem because the number that Kelvin came up with was 20 million years. That's how old the sun was. And this is a problem because there was plenty of geological evidence. You know, Darwin had said the Weald in Kent was 300 million years old. So Kent was a lot older than the sun, which just couldn't be true, right? And the evidence was accumulating. And it's one of those cases where evidence has to accumulate a lot before people give up their theories and shift their theories to something new. And so enter on the scene in the British Academy of for the Advancement Association for the Advancement of Science. Their 1920 annual meeting in Cardiff, Sir Arthur Stanley Eddington got up to give the president's address. And he took as the topic of the president's address the internal constitution of stars. And this was, Eddington became very, very famous for his work on this. And it's one of the great public lectures on science, because not only is it a public lecture on science, but he actually reveals several things that had never actually been published before in this lecture. You can read it, actually. It was published in Nature, and the sort of delightful Victorian English is great fun to read, a little pompous and to our modern day ears. I'm sure it wasn't pompous at the time. But one of the questions he addressed is, where does the energy radiated by the stars and sun come from? Because he starts this by pointing out the sun can't possibly be 20 million years old. There's all kinds of astronomical evidence, which I won't go through, but it's worth reading, right, at the time, that the sun must be billions of years old and not 20 million years old. And it's one of those nice things in physics where it's not a whole bunch of equations and things like that. It's just logic and just understanding and putting the question in the right way. He runs through all these and he says the sun must be much older. But if it's older, where does all that energy come from, right? Why does the sun continue to radiate if it's much older than that? And he was lucky. You know, in science, being lucky might be more important than being smart sometimes. And he was lucky because just the year before, Aston at Cambridge had really got mass spectrometry better. And they're able to measure the masses of hydrogen and helium and many of the elements with great precision. And when he did this, he discovered that the mass of hydrogen is tantalizingly close to 1/4 the mass of helium, but not completely close. And so Eddington sets out and he says, you know, if we have a process that converts 4 hydrogens into helium, and of course to do that, you have to, I love to wander around when I'm talking. Helium has 2 protons, 2 neutrons. So 2 of the electrons that were on 1 hydrogen have to be somehow captured in the nucleus. And he makes this remark. But if you do that, we know how much energy is released, because we have a certain amount of mass to start with, and we have a certain amount of mass at the end, and the missing mass is the energy that's released in binding this together. And you can calculate that just knowing that E equals mc squared, the most famous equation in physics. And he does that, and he says, you know, if you made some reasonable assumptions about how much, turning of hydrogen into helium is happening in the sun, let's estimate its lifetime. And he comes up with 15 billion years, which is a pretty good estimate given all the uncertainties in this calculation. It's pretty close to the lifetime of the sun. That's indeed what's happening in the sun. And what's interesting about the logic here is that he didn't actually have to know very much nuclear physics. In fact, in 1920, we didn't even know there was such a thing as a neutron. right? I mean, he was just using E equals mc squared and deducing that there must be some missing energy here and that would be powering the sun. He invented nuclear fusion. In the paper, he speculates that, in fact, this is the way all the elements are made inside stars, by joining them together, and basically, as he says, all constituted from hydrogen at that time. It's a marvelous lecture. He may not have been the first person to actually have thought this, but he was certainly the first person to articulate it in such a clear and beautiful manner. And he goes on to say, this reservoir can scarcely be other than the subatomic energy which, it is known, exists abundantly in all matter. We sometimes dream that man, these were fairly sexist days, will one day learn how to release it and use it for his service. The store is well nigh inexhaustible if only it could be tapped. So he's saying that process in which you join smaller atoms together, which we call fusion today, right, could be used as a power source in the future. And it's sort of prophetic. Well, it's not prophetic because we haven't done it yet, actually, but you know, it's a rather nice quote at that time. So after that, you know, there was a period in the late 1920s and the 30s in which the nuclear physics of what was actually going on started to be all worked out. But the idea of tapping nuclear energy really is a Second World War thing, right? And we've all been to see Oppenheimer, I suspect. The British are downplayed in Oppenheimer far too much. The only British that really is featured is Klaus Fuchs, who was a spy. So, you know, we want more credit than that. But at the end of the Manhattan Project, in the fall of 1945, after the bombs had been dropped, and they're all about to return to their universities to resume their academic careers, they had a DMOB conference at Los Alamos. And this DMOB conference was basically all the luminaries at Los Alamos talking about what they thought they would be doing in the next decade or so, and what was important maybe to the US government. So some of it was about weapons, and some of it wasn't at this conference. Some of it was about things that people thought would be important in physics coming up at that time. But the conference was entirely classified. You weren't even allowed to take notes in this conference. It was in November of 1945. But in November of 1945, the British government had figured out that you guys were not going to let us see your nuclear secrets very shortly. In 1946, the American government passed the McMahon Act, which banned Britain from knowing nuclear secrets of the United States. And we had been totally collaborating on the bomb, so we knew a lot of nuclear secrets already. But what the British government was doing in the fall of 1945 was telling the British contingent in Los Alamos to take notes and to keep those notes. And the most important of those notes was Klaus Fuchs. He didn't just spy for the Russians, he spied for the British in some sense, because those notes that he took, that he handed to the Russians, he also used to lecture to British scientists after the war. But the point here is that Fermi got up and gave a talk about fusion. And most of the talk was about the fusion nuclear physics of the fusion of deuterium and deuterium and deuterium and tritium. We'll get to that in a moment. And the end of it was, so if you wanted to do controlled fusion, how would you possibly hold something at the conditions similar to the center of a star? It has to be so hot that you're talking about tens of millions or even 100 million degrees, right? How are you going to hold it? And Fermi talks about confining plasmas in magnetic fields, which is what I've spent my life trying to do, at the end of this talk, right, in 1945. So it's a bit depressing, really. Everything goes back to Fermi. And he was a marvelous physicist. But the reason is, I'm showing you this. This is a classified report. These were the notes that a guy called Philip Moon, who was part of the British contingent at Los Alamos, took and handed to a gentleman from the British Diplomatic Service later that week, right, and was brought back to Britain as an intelligence document, which was notes on the lecture by Fermi. These are the only notes we have on the lecture by Fermi because everybody else was banned from taking notes on the lecture by Fermi. They were declassified at the end of the 1950s or the early 1960s, and so you can see it scrawled on it, declassified. I'd heard that this, what Fermi showed actually at the end of this thing was that you couldn't confine a plasma just in a circular magnetic field. So what we call a pure toroidal field was not enough to confine a plasma. And in the early days of the Princeton lab, that was known as Fermi's theorem for reasons that the old-timers tell me they didn't know. He proved it in this lecture at that time, and it was an important component of the design of what's called the figure-8 stellarator, which launched the Princeton lab in 1951. Right? And so understanding of Fermi's role as sort of disappeared in the mists of time. And then in about 2012, Dan Cleary, who's one of the senior correspondents of Science magazine, gave me a call and said, Steve, I think I found a document that you'll be very interested in. And he found this document in the library at Churchill College, Cambridge, among Sir John Cockcroft's papers in the library, and then I understood what it was that Fermi had done in 1945. That started our field. That's what started us thinking about confining plasmas with magnetic fields to make fusion happen. So the first question is, we're actually in a moment in which the US government is getting very excited about trying to accelerate the development of fusion. We've seen $6.2 billion in venture capital investment in fusion companies in the last 4 years. That's phenomenal amounts of money for a technology that's at quite low technology readiness level. Why are we this excited, right, about fusion? Why would we think that fusion right now is in a state that we want to move forward in a more accelerated way? So I think there are two reasons for this. And the first one is the need. Right? Why do we need fusion? If you know about the energy systems out there, renewable energy is coming down in price in very pleasing and dramatic ways. I mean, the cost of wind energy, the cost of solar energy, of just, photovoltaics are going down in price, wind energy is going down in price. This is very good for our planet, right, that this is happening. But total decarbonization of our energy system requires more than renewable energy and its intermittent output. I'm more familiar, because I did a bunch of things for the British government on this, about the intermittency of wind and solar in Britain. First of all, solar's totally intermittent in Britain. You can forget about that. There's a problematic month, really. It's December, when energy demand in Britain is very, very high, but there's no wind. It's curious that in the middle of winter there's no wind, and there's no wind even on the shallow sea where we have the offshore wind in Britain at that time. So this intermittency makes it very hard to go to 100% decarbonisation of your energy systems. And we all know the arguments, maybe we need storage, maybe etc. But there's a lot of analysis of this. And so this is a typical analysis by the group at Princeton at the university under Jesse Jenkins and others, and we've been participating in this. Looking at this is for an area of the United States, and looking at the cost of reducing your CO2 emissions in your electricity generating system. And on the left-hand side, they have two kinds of energy generating system. Fuel saving, which is solar, wind, and hydropower. Fast burst is energy storage and flexible demand, and the assumption here is that your energy storage can store for short amounts of time, but not for long amounts of time, which is typical of batteries on the grid at this point in time. And what you'll see, we start here with roughly where we are, with no mitigation of your carbon emissions, and step it down towards zero carbon emissions there. This is the price of your electricity per megawatt hour in dollars. And what you see is the first bit of decarbonising your energy system doesn't cost you very much money. The cost of your electricity doesn't rise steeply. But as you get to try and go to 100%, it rises extraordinarily fast. if you only have these kind of energy systems on your grid. However, if you have something like nuclear, gas turbines plus carbon capture and storage and sequestration, or bioenergy or syn fuels, this firm low carbon, right, component can keep this from rising strongly as you try and head for net zero carbon emissions in your system. So the need for what's called a firm energy source is well recognized in the energy community. We had a meeting at Princeton in January of 2022 when people came from the Office of Science and Technology Policy in the White House to talk about whether fusion was ready to move faster. And part of the argument is that the acceptability of building large-scale amounts of nuclear fission is not clear and not politically easy for the administration or their successors, I think, to see. So the need for fusion to fill that gap, the firm energy gap, to provide this accessibility to zero carbon, not just a reduction in our carbon emissions, but zero carbon, was absolutely paramount in their mind. That's why they came to see us and said, you know, what could we actually do and how fast could we do it? So I think of that as the sort of demand signal for fusion at this point in time, right? We need more firm energy sources, and we need them as soon as we can get them, and I'll get to timescales in a moment, but that is the argument on that time. The other is the interest. I think the third, of course, is that we've actually had some good results, which indicate that we might be able to do fusion. But the interest has been phenomenal. This is the Fusion Industry Association members. This is where $6.2 billion in investment in 4 years in fusion startups. I have to say, a good fraction of which are somewhat bonkers. That's a technical term, it turns out. I was actually asked by a senator whether it was a technical term. I think he was being ironic too. But some of these are very exciting companies doing exciting things, developing technology for fusion, some of them developing fusion concepts that have not been looked at before, some of them heading straight down the main line of fusion, and I'll talk about that. The main line of fusion being what we call tokamak reactors that have been tried for, now something like 50, 60 years. But, this is an exciting time, and I think quite a few of colleagues here at UCLA are collaborating with these companies. We're collaborating at Princeton with 15 of these companies. There's a lot more than 15, but, we only have a certain amount of capacity. A lot of these companies are capitalized at a few million. The largest capitalization is $2.2 billion for Commonwealth Fusion Systems out of MIT. This is a pretty exciting thing. So out of that meeting in January of 2022, we had a summit at the White House. This is just me boasting, basically. It's me standing in front of the White House. I'm the person with the brown hair. And this was to discuss sort of what should be the aim of the US. See, up to this point, the fusion program in the Department of Energy had this aim. Their aim was to develop the science of fusion and plasma physics, but not to develop an energy-producing reactor, right? It had been since the middle of the 1990s. They had dropped the idea that we were in an energy program. We were in a science program, and we were going to develop the science. And this summit basically shifted that, not just perception, but reality. Right? Actually having as your goal that we're going to produce an electricity-producing fusion reactor at some time. And the key document is this document from the National Academy called Bringing Fusion to the US Grid. And that document basically said this: the Department of Energy and the private sector should produce net electricity in a fusion plant in the United States in the 2035-2040 timeframe. I believe that is a stretch goal, but it's the goal that we should have to actually make some electricity in that time. I know that I'm looking at my colleague right here, Mohammed Abdu, who's one of the great fusion technologists in the field, and I think he thinks it's a stretch goal too, maybe more than a stretch goal. But we've got to set ourselves up, because actually we need this firm energy source sooner rather than later. Now, the private companies have goals like, for instance, Helion Energy out of Seattle has promised to deliver fusion electricity to Microsoft by 2028. If that happens, I may have to eat my hat, but it's ambitious, and they're smart people, and stuff could happen, right, on that timescale. So the response of the US government has been to set up programs that are going to help these companies. A lot of the companies don't have a lot of technical depth. They have good ideas, but they have a handful of people, etc. And so they've set up a milestone-based program. This is sort of based on SpaceX-type programs where the government pays you money if you meet one of your milestones out of this. And there are 8 companies that actually won in this solicitation. They've still to really finish the paperwork, to be honest, because it's very hard to come to an agreement on IP and all of those sharing things at this time. So this is a challenge at the moment, but these 8 companies are in the milestone-based program. We're collaborating with 7 from Princeton, providing theoretical tools to them, providing simulation capability, providing diagnostics, providing all kinds of things to these. They're pretty heavily capitalized, these companies, and I think somebody was saying their child was working for Zap Energy. That's one of the milestone-based the programs at this time. So I always give a talk like this. I don't put the introductory slide until about 5 slides in. I always tell the graduate students that this is like a James Bond movie. You know how the start of a James Bond movie is always him on top of a train, they're going into a tunnel, things like this. You haven't seen the title yet, etc. And there's a bit of excitement, you draw everybody in, and then the title comes later and the blood drips down the screen and everything else like that. It's a technique. So this is the declared plan, right? That we should be, by the end of the 2030s, actually making some electricity from fusion. It's not clear what anybody means by a fusion pilot plant, right? Making some electricity, yes, but does this mean, kind of net electricity? Does this mean substantial amounts? Is this a prototype of a commercial fusion power station? What is this, right? There is no official answer to that. You'll get my answer, of course, but there's no official answer. Can we build a pilot plant with today's knowledge, right? With what materials? How, right? Those are difficult questions, and actually, those questions don't really have proper answers, which means we don't know whether the materials we have are the right materials, etc. I'll give you a personal view. This is not a DOE-sanctioned view. It's not even a Princeton-sanctioned view. It's probably get me into trouble, all those kind of things. So let's go back. And, some of you in the audience probably don't really know what we mean by the fusion reactions that we mean. So what is it, right? So when you think about, there are really only 2 forces important in this. Right? There are 2 forces that dominate this process. One is the fact that nuclei are charged, because the protons in the nucleus are charged, and they repel at distance. When you get them close enough together, another force comes in, which is the strong force, which binds the protons and the neutrons together inside a normal nucleus. And so what happens, of course, when you do fusion is you bind one nucleus to another nucleus and make a bigger one. And the easiest fusion reaction to do is between deuterium, which is heavy hydrogen. That has a proton, which is green in the pictures, not in real life, and a neutron, and tritium, which is super heavy hydrogen, which has a proton and 2 neutrons. And if you ram them together sufficiently hard, at distance, they repel each other. At distance, because of the charged particles, repel, they get close enough to each other, the strong force will bind them together. And for an instant, they form helium-5. In this case, for the physicists in the audience. They form helium-5 and a metastable J3 halved state of helium-5. And then they decay into spitting out helium and a neutron, both with copious amounts of energy. They have kinetic energy. So basically, the result of this is the heat in those particles, the kinetic energy of those particles coming out. This, by far, is the easiest fusion reaction to do, actually because of the resonance with the metastable state of helium-5. Right? And it has one problem, well, apart from the fact in order to ram them together, they have to be moving at speeds comparable to an equivalent temperature of about 100 million degrees. You have them running around. Every now and again, they bump into each other. They just glance off each other. Every now and again, they bump into each other just right, smack on, and they fuse. Right? Apart from that, the problem is that tritium doesn't exist in nature. It decays. It's 12.4 years, 12.3 something years is the lifetime of tritium. And so you have to make it. And you make it by bombarding lithium with the neutron, which causes lithium to split into helium and tritium, and you take that tritium and you put it back in your fusion reactor. So this bit here requires temperatures of something like 200 million degrees. That's the typical temperature when we've done fusion in the middle of our device. It's about 200 million degrees. We always used to say Princeton was the hottest place on the planet. I like that. But in order to make this happen, you also have to have a step where you breed that. And that happens in the walls of your device in what's called a blanket, and we've never made one of them. Right? So that step in the fusion process has never been made. We've made tritium for other purposes in nuclear reactors, but we've never made it in a fusion system. There's enough lithium in the sea, there's 0.2 milligrams per liter of seawater, to power the world for 30 million years, which is great. There's also enough deuterium in seawater to power the world for 60 billion years, which is longer than the lifetime of the Earth, so that's great too. And so this would be a wonderful reaction to do. The byproduct, helium, right, is very inert, fine, it's great. The process we don't do it with have relatively little safety issues. Nobody should say we have no safety issues. Some people do, but it's the wrong way to approach it. We have safety issues that may be managed, right? And that that it doesn't produce any high-level nuclear waste unless you put silly things in the walls. So it's almost the perfect firm energy source, except the business of getting 200 million degrees and actually taking it out of there. The power from this reaction, and I'm going to show some equations. So like all of my talks, I start sort of with a little history and I build up and stuff, and by the end I've confused everybody. So I'm getting there. So simple approximation to the power that you can generate from this. So if you heated some deuterium and tritium up to something like, this is kilovolts. So this is 100 million degrees. This is 200 million degrees. And in that sort of temperature range, the reaction, if you heated your deuterium up to those temperatures, you would get a power, this is in megawatts per meter cubed, coming out of your plasma from your fusion reactions, that is basically, well, it's 0.08 times the pressure squared in atmospheres. And I use these units. I know we don't like to do this with students, but you want to adjust your units so numbers are like 1. So I've adjusted the units so the numbers are like 1. Megawatts per meter cubed for a 50-50 mix. So what you need is a nice strong pressure of your plasma in the center. And the typical pressures we get in our devices might be a few atmospheres. In the center of ITER, the device we're building in southern France, the pressure will be about 7 atmospheres of pressure. So then you would be talking about, basically about 4 megawatts per meter cubed inside your plasma, and a plasma volume of about 1,000 meters cubed. So you gigawatt of power, a few gigawatts of power coming out of your device. That's about the scale of what you want for a reactor. So this reaction, actually, people in the early days did these simple calculations and said, yeah, it might work. We might be able to make fusion this way. How do you hold something at 200 million degrees? And this was what Fermi was asking. Right? You put it in a magnetic bottle. And this is the conventional device. There are a number of different concepts being explored, but this is the conventional device. It's called the tokamak. It was invented by Andrei Sakharov in the Soviet Union in 1950. And it's basically a bent solenoid. So these coils produce a field that goes around like this, right? And this coil down here changes the magnetic flux through the middle, so we induce a voltage around the loop, Faraday's law, and that voltage drives a current in the plasma that goes around the loop. Now the simple thing is, you remember this from high school physics, like currents attract. And so what happens here is the current on one side of the column attracts the current on the other side of the column, and it attracts itself. It's somewhat narcissistic. And so the whole column of plasma pulls itself off the wall and isolates itself from the wall. And it's that magnetic confinement that provides the best performance that we've ever got there. And a figure of merit is how much pressure of the plasma you can get for a magnetic pressure. The magnetic pressure in, again, my handy-dandy units in atmospheres is 4 times B squared, where B is measured in Tesla. And typically in the plasma, we might do something like 5 Tesla in the plasma in these devices. And so that is 100 atmospheres of magnetic pressure on your plasma. And that's what holds it. That's what holds it in the middle from escaping. And so back in the 90s at Princeton, we had a machine called TFTR, the tokamak fusion test reactor. This device, there's a picture of it, in 1994, fired up to a temperature of about 250 million degrees, and they got a burst of fusion power, right, for 1 second of just over 10 million watts. In some ways that's really impressive. In some ways you go, well, it was a second, right? I mean, etc. But the temperature was 250 million degrees. We got the conditions for fusion. It was really quite a spectacular day for fusion, right? And later, this device, JET, down here, this is a device at the lab I used to run in the UK, produced this 16 megawatts of fusion power for just over 3 seconds. And then this, which actually is more relevant, which is the device can fire for about 5 seconds in total. So you fire it up for 5 seconds and hold it at 4.5 megawatts of power for 5 seconds and then shut it down. That's a nice, not a burst of fusion power, but an actually sustained fusion power at that time. And those were the records till quite recently. And then while I was in the UK, I argued we should repeat these and do better than these shots. And so JET, during my time, we got permission to buy some more tritium. You buy tritium from the Canadians. They make it in their nuclear reactors as a byproduct. And it costs $30,000 a gram. We bought 56 grams. It's quite expensive stuff. We bought 56 grams of the stuff. And because progress wasn't as fast as we hoped, in fact, that run with tritium happened after my time, and my successor has done it very well. And this was the record. Basically, this was that 4.5 megawatts of power for 5 seconds. This was what happened in the campaign, what we call DTE2 in 2021, was 59 megajoules, and it was an average of just around 10 megawatts for 5 seconds. And this, 69 megajoules of energy, right, was just in December of 2023. And we've closed JET, and it's done its job, because it showed us that we can get the conditions for fusion and we can make it happen at that point. So the next step is what we call burning. And when you do the fusion reaction, I didn't point it out when we showed it, you get an alpha particle, which is a helium nucleus, come out. That's a charged particle, and it runs through the plasma, banging into the deuterium and tritium, giving its energy to the deuterium and tritium. So the fusion reaction can heat the plasma and keep the temperature hot. And in none of these devices did we get that, right? We got a bit of it, but not enough to keep it hot. It was leaking energy too fast to keep it hot at that time. So this is the machine we're building in southern France. It's an awesomely sized machine called ITER, and it's an awesome budget too, actually. This device is designed to do this, what we call the fusion burn. But this is the main line to fusion, and I think what we're seeing at Princeton is that we don't believe that this main line will take us directly to commercial fusion. We've got to bring down the cost and the scale of fusion to something that could enter the US market with any realism. This device is going to cost over $25 billion to build and won't actually produce any electricity at all. So what we're doing at Princeton is trying to invent devices, and we've got one that we're just rebuilding right now, which will bring down the cost and scale of fusion. This device is called the National Spherical Tokamak Experiment. And that's the device on the left. We're just building an upgrade of it, and the one on the right is a reactor concept based on it. And the UK government just funded a program to actually design a reactor based on this concept for the UK, which we're collaborating with too. So what happens when you get a self-heated plasma? This is an interesting set of simulations of what we think ITER might do. So what you do at the beginning of this is you have this donut-shaped vessel, and you puff in some gas of deuterium and tritium. You turn on your magnetic fields, and then you change the flux through the middle, which drives a current round the loop and starts your plasma. And that's here, in this first period here. At this point, you're driving about 15 million amps around that loop, and it starts to attract itself, and it pulls itself into the middle and holds it together. And then what you do at this point here is you turn on heater beams. These are beams of neutral particles that slam into the plasma and heat up the plasma. Then the temperature goes up from a few tens of million degrees right up to 200 odd million degrees. And this is your heater power coming in at about 70 megawatts of heater power. Now the scan that's based on the best model, these are all different models. And it emphasized the fact that this is an experiment, right? The scan that the best model is the blue line. On that blue line, what happens at this point is you start getting fusion power. This is up to about 600 megawatts of fusion power. You're putting in 70 megawatts of heating power, right? You step down your heating power to 50 megawatts at this point, and at this point you turn off your heating power. And what's happening when you're doing this is, although you've got 600 megawatts of fusion power, 4/5 of that comes out as a neutron. 1/5 stays in the plasma and heats it. It's the charged particle that's released in that. And so what's happening here is it's self-heating exceeds greatly the external heating you're doing. And in fact, at this point, it's able to sustain the discharge without any external heating at all. That's called ignition. And these predictions of ITER's performance, we don't know if they're true. We haven't done the experiment yet, and these are predictions. And if you change the boundary conditions, you get a different result. This one, for instance, would be okay. It would ignite, but at far less power. This one here is scan 4. As you're producing your fusion, you're making helium inside the plasma. If the helium builds up, you've essentially got an ash. It's like, you know, building a fire that's got too much ash in it, and you can't get the wood to burn, right? And what happens is it goes out at that time. This is what that experiment wants to do, right? I will, about 5 more minutes. Is that okay? How much more have I got? 45. Okay. I've got enough material, don't worry. How does the heat get out? Because the point here is you've got this self-heating from the fusion, but the heat is leaking away, so your plasma would cool down if you didn't have the self-heating. So you need the self-heating to defeat the way the heat got out. And the history of my career in this has been we've solved the problem of how does that happen? And it happened in a good part due to work that was done here at UCLA, right? Now, when I got into the field in the early 1980s, we knew there was turbulence inside the plasma. We knew that what was happening inside the plasma, let's see. Oh, sorry. I'm trying to find how does this work? Must be there we are, good. We knew that was turbulence inside the plasma. The middle of the plasma is at 200 million degrees, and the edge of the plasma is a wall, right? And that's if you're lucky, 10,000 degrees, close to the wall. And there's this huge temperature gradient across the plasma that drives convective turbulence. I mean, it's just like, your saucepan on the hob, right? The stuff on the bottom's hotter than the stuff on the top, so it rises. And the stuff on the top falls, and you get turbulent mixing inside your saucepan, right? Same thing happens inside our devices. But the success has been to make that turbulence very small scale. So each time you have these turbulent eddies, this is the density perturbations action. These turbulent eddies cause little swirls of plasma that are elongated along the magnetic field lines. And this turbulence that's driving it's actually unstable. It's kind of unstable sound waves. Causes the hot stuff to work its way out, and the cold stuff to work its way in. And that loss of heat due to that process was what's dominating our experiments up to now. And the success has come to try and minimize this turbulence, right, in our experiments. This was something. We needed to do two things. We needed to figure out how to calculate this turbulence, and we needed to actually verify that was what was going on inside the devices. And UCLA played a big role in this. When I came to UCLA in '93, the calculations weren't actually working terribly well. And one of the people I want to pay tribute to is my great friend Bill Dorland, who really made these calculations work. We have to calculate this turbulence inside of a plasma, which is a collection of charged particles all whizzing around the magnetic field lines and bubbling away. And he came up with a bunch of algorithms that actually made possible to solve those equations in 5 dimensions in space, right? And these calculations are now routine. We can do them on machines, but it's more than that. We needed to show that that's actually what's going on inside the machine. And this was sort of one of UCLA's sort of specialties, which was being able to look inside of a plasma and measure what was going on inside these very, very hot plasmas, particularly with microwaves and stuff. And so Troy and his students played a big role, particularly people like Ann White, who's now at MIT, in actually taking the results of the calculations and taking the data from the experiments and saying, yeah, that's right. We're getting the right thing out of our codes. We're actually able to do that. And I want to also pay tribute to Tony Peebles, who was the UCLA diagnostics group lead in my time here, whose microwave measurements on D3D and other places were part of the solution to this problem. That works. Right? Those calculations now give you detailed, and I will just give you a taste of actually what's actually happening. It turns out what the turbulence does is it basically makes a random walk of heat from there to there. And we know about random walks. Basically, the distance you go is proportional to the square root of the number of steps times the step length. And these eddies inside the plasma are roughly a llama radius of an ion. That's the helical radius of an ion going around the magnetic field line. And therefore, the number of steps that you make in the turbulence is the size of the device divided by this llama radius. And if you now say, okay, how long does it take to make a step? Because a random walk is, I take a step forward, take a step backwards randomly, and I'll work my way out of the system. And it takes about these bubbling turbulence is about the eddy turnover time. That's the time it takes it to make one of these steps. It's about the size of the device divided by the velocity of the ion going around the device. So if you put that together, the number of steps you have to take to get out of the device times the eddy turnover time, you get that it scales like the square of the magnetic field times the cube of the size of the device times the temperature to the -3 Hz power. Well, to do fusion, the temperature has to be about a fixed number. So all the machines that you want to build basically are going to fall on this kind of line, right? Now, the trick up to now has been to do better, to reduce the turbulence, to make the step size smaller, to make the turbulence less virulent inside it. And we characterize this by a number which we call H, right? H varies between 1 and about 2.5. Actually, it varies between 0.5 and about 2.5. We never mentioned the stuff less than 1. And actually comes into the answer cubed. So 2 is 8 times different than 1. I've forgotten how to count. But this is the basic law of how the stuff gets out of the device. And if we want it to ignite, sorry, we're getting into the physics here. I told you I'd confuse you before the end. We have to have the heating, which I told you is proportional to the pressure squared, balance the loss of energy from the device. And now we have that time that it takes the heat to get out. Loss of energy is basically the energy stored divided by the time, right? That gives something called the Lawson triple product. It says that in order for you to be self-heated by the fusion, the pressure times the energy confinement time has to be bigger than typically it's about 10 atmosphere seconds. That's the basic rule that you want to do, right? And what that does, I've got these handy-dandy formula. I put that in there. I put the pressure in terms of the magnetic field. I come up with the universal law of fusion devices. It says that I have to get, this is what magic I do to the turbulence. This is the strength of the magnetic field to the 4th power. This is the radius of the device cubed. Has to be bigger than some constant. And if you look at all the devices we've ever made, they basically fall on this line. There's an empirical law we call the H-mode scaling, and it's almost exactly this, which is just fitting all the devices to this. And this is what took over on a report to the National Academy in about 2017, just before I got to Princeton. People said, you know, we're going slowly with ITER. It's not coming soon. So can we do something fast and better? And if you look, right, we would like to make things easier, smaller, etc. And so one of the things on this, let's go back to this, is if I make the field stronger, I could make the size smaller. We've known this forever, but it's obvious, really. And the coils that we put around the plasma these days are made of superconductors. So could we double the field, triple the field inside it and make a much smaller device and therefore perhaps easier to build and cheaper to build? And this came off in a number of reports. The first was actually from our lab, but now this company that spun out of MIT is hoping to build a device that has about 2.5 times the magnetic field of ITER in it, in order to make a machine that's, you know, much smaller at that time. One thing I would point out, the total fusion power has a very similar formula because it's proportional to the pressure squared. And actually, if I make a smaller device, I don't change the total power. I change the power density because the magnetic field allows me to go to higher power density, but I don't actually change the total power coming out of the devices. So this proposal, this is the self-similar scaling. This is the device ITER that's being built in southern France by 7 international partners. It has a radius of 6.2 meters. It has a B field of 5.3 Tesla. And this product from that self-similar scaling is about 20. And the device proposed by Commonwealth, MIT and the Commonwealth Fusion Systems company, Spark, has this radius, much smaller, right? And has this magnetic field, 12.5 Tesla, immensely strong field inside the plasma. On the coil, it's 23 Tesla, which has a pressure equivalent to about 2,500 atmospheres, which is 2.5 times the pressure at the bottom of the Marianas Trench. So this is some set of magnetic coils if we can make them work. But it has exactly the same self-similar size, basically, to ITER. It's a machine very like ITER, but the company is trying to accelerate that process by making a smaller machine, but at technologically very difficult high field. So this was what propelled, in some sense, some of the optimism that now with high-temperature superconductors, maybe we can make coils with this field. And this company is going at it hell for leather at this moment and may, in fact, make some of the most impressive superconducting coils we've ever seen at that time. But it doesn't come for free. If you up the magnetic field strength, the power density inside your device gets really immense, right? But the power density becomes a problem. Because how do you get the heat out of this plasma? The turbulence is bringing the heat from the middle to the outside. And when it gets to the outside, we have what we call the scrape-off layer. And it's magnetic field lines that go and hit the wall. And then we have pumping right around here that pumps away the plasma. So here's your turbulence, it moves it to the wall, it goes along the magnetic field and goes up there. Now, in devices at the moment, we get about 10 megawatts per square meter on that piece of wall. That's about the limit of what materials can take. In the devices that we're building, it's hundreds of megawatts per square meter on the wall. So the proposal is that we interrupt this by putting neutrons close to the wall here that radiate away the temperature. But the problem is, it has to radiate something like 96% of the heat coming towards the wall invariably, because the moment that actually hits the wall, that heat, it will melt the tungsten on the wall and our device will not work anymore at this time. So it doesn't come for free. It might be the way forward, but there's trouble there. I'm going to say a little bit about making electricity, and then I will give you what I think was one of the most exciting things happening. When we make electricity, we have to do a lot more than just make fusion happen. You make fusion happen inside here, and the heat comes out, and in the wall, you make tritium from lithium. And the wall gets hot, and you make hot water, and you power a turbine. I always say that fusion is a very expensive way of having a steam engine, basically. That heat exchanger, that blanket, never been done before. The neutrons that are coming out here are damaging the wall, the structure. There's a whole technological challenge of actually doing this bit of fusion. And not just that, you have to take the tritium, which is made in the wall, out, purify it, and get it back in your plasma. And Professor Abdu has been very eloquent about the fact that this is going to be an enormous challenge to us. We've not done any of these steps at this time. And the idea is that a pilot plant would come forward and do this. So what do I think a pilot plant will have to be on that time scale? I mean, it's going very fast, even to get it by the end of the 2030s. It will have to be, right? It can't be a prototype of a commercial reactor, because we've never tested the wall, we've never tested the blanket, we've never tested the materials that go in the wall and all these things. It has to be a test reactor, right? It may make some electricity, but it has to be a test reactor. And so it will be a reactor to test the materials, the systems, etc. that go in. Now, I think politically, it'll have to make some electricity. Exactly how much electricity, I'm not sure, right? Because I think that will set in motion people understanding that this is really real, right? But this is very like Mohammed's volumetric neutron source that he's proposed for years, that we should build something like this to test all these technologies. I'm just saying, add to that, make some electricity, and that's probably the machine that we should aim to build at the end of the 2030s. It's not the machine that the companies are saying. The companies are saying by the end of the 2030s they'll be marketing commercial fusion reactors, etc. I don't think utility will build anything that hasn't operated for many years and been maintained for many years, etc. And I think it's unrealistic to start putting up a target that suddenly will make a reactor that works for a few months, and then the orders will roll in from the utilities at that point. So this should be our goal at that time, and I have to thank Mohammed for essentially inspiring this slide. But I'm very excited about something, and it comes out of the work we did here at UCLA and the work during the 90s and the 2000s and 2010s, which is we have models now that actually calculate what goes on inside these machines. That science didn't exist in the 1980s. And it grew slowly, and it's accumulated with time, so that we have predictive models that can tell you what will happen in a future device, that we have some confidence works. In other words, the scientific program kind of worked during that time. And a bunch of the early career people, I'm not allowed to call them young, early career people at the lab and the universities have started to come up with new designs. These are three-dimensional designs called stellarators, which have a property called volume quasi-symmetry. It's a beautiful property that means that the plasma is quite kind of well confined inside here. And Elizabeth Poole on the top right-hand side is a new assistant professor at Columbia. Matt Landerman is at Maryland. Felix Parra is our head of theory at PPL. We pinched him from Oxford. These designs are in the minds of theorists. But we can run all our codes on them. We can test out how they would actually behave, and we can look for optimum solutions. So what we're doing now is we're searching the space of billions of configurations for a configuration that would give the best performance in a fusion reactor. Using AI tools, using high-performance computing, this is going to be a very exciting process. And out of that, this guy, early career person, Noah Mandel, he sped up the turbulence codes by a factor of 100, and they're now in the optimization loop so that we can actually do this. Back in 1951, this is what Lyman Spitzer proposed as a fusion device to the Atomic Energy Commission that started the Princeton lab. Right? That's a stellarator. The latest stellarators, this one on the top right-hand corner is Thea Energy, which is one of the startups in the milestone-based program that has a radical concept for the way you make the magnetic field inside there. That's David Gates, who came out from our lab, who's the chief technology officer of that things. There's all kinds of ideas coming out of this. The science has got to the point that we're ready to use the science to explore the space. And so this is something I'm very, very excited about, because we might find optimum fusion configurations, maybe the first time that AI has solved a major technological problem in the world. I think fusion's needed, not just wanted. It can be delivered, but the challenge is immense and shouldn't be underplayed. I worry that sometimes expectations have been raised too high by some of the hype that goes on. The real progress has been in the science. The fact that we understand things that before we only had an empirical law for is spectacular. Right? We should aim for first electricity between 2035 and 40, but it's a stretch goal. Thank you very much for your time, and it's delightful to be here.
Thank you, Steve, for that excellent talk, as always. I'd like to open the floor up for questions. What questions do you have for our distinguished guest? The trick is you have to wait at least 7 seconds, so somebody raise their hand. There we go. Thank you. Jason, go ahead.
Great talk. I have a detailed question. You showed some plots of output power as a function of time with these 5-second burns. Even for runs that were separated by a few years, the sort of fine structure of those output powers track each other. Does that point to some instability, or what's the understanding of these data?
The detailed structure in there is that those plasmas are not being heated by the fusion, they're being heated by beams, largely. They're being heated a bit by the fusion. And the beams come on and they go off. right? Because we can't sustain the beams through those certain times. So the bumps and stuff are bumps and wiggles in the beam power going into the plasma, largely. I was trying to get that, during my time there, I was trying to get those beams to be more consistent, but we never really succeeded, to be honest. Yeah.
What other questions? Please.
Well, you say our aim should be to produce the first electricity. So we haven't produced any sample of electricity up till now?
No.
And what would be the level of electricity that would be satisfactory to prove this?
So that's a very good question. In some sense, when you make a test reactor, you don't make it to make electricity, you make it to test the technology that you're doing. And so any electricity would be nice, but I don't think it would be impressive enough to keep going unless that were significance in the hundreds of megawatts. So fusion works better the bigger you are, really, because of that law b to the fourth times r cubed has to be bigger than a number. And so optimum size reactors at this point are probably almost a gigawatt electrical, which is a big power station on our grid at this point.
Are there other variables in the process that you could train AI to address that may result in a stride similar to turbulence forecasting?
I'm told, and I didn't talk about laser fusion, and they made these amazing steps forward with the NIF program. And just recently announced another record-breaking shot on the NIF program. I'm told that what they do in the NIF program is actually use AI to predict performance based on various things they measure about the capsule, the roughness of the capsule and various issues, and on various other parts of the system. So that's been done. I think, we're not going to challenge the tech companies on making large language models, right? What we're going to do is we're going to use, as they did in the protein folding problem, we're going to use AI to miss out steps in calculations, and that's what we've begun to do. And what AI does there is if you're running huge numbers of calculations, bits of which are complete repeats of previous ones, if you've been training on those simulations that you did in the past, you recognize that at this point in the calculation, you've seen this before. And you know how to predict 1,000 steps into the future, right? And so using AI, you can suddenly, in the middle of your optimization, use an AI to shorten that calculation by a huge amount. And this interaction between AI and high-performance computing, I think, is where the labs can really contribute.
What is your perspective on the practicality of ICF as an energy source?
It's too early to say what's, preferable. I always get asked by the journalists, are they ahead of you or are you ahead of them? Actually, sometimes I'm not shy. But I think there are challenges in ICF, but there are also advantages to ICF. So ICF is inertial confinement fusion. This is where you make a little capsule of fusion fuel explode, basically, and release all its energy at once by compressing it with a laser. And one of the advantages of that is that the fusion is a long way from your high-tech object, which is your laser, right? And therefore, you're able to engineer, in some sense, a lot of the nuclear components without having to worry that those nuclear components are inside superconducting magnets, inside, all this kind of thing. So there, in my view, we don't know whether inertial fusion will get there. The idea of having, one of the great things about the stellarator, for instance, is that you need no recycling power. So when you do laser fusion, you have to put power into the laser in order for it to make fusion. And if that power is too much on the round trip of making fusion, making electricity from fusion and then going round, you haven't made net power, right? In inertial fusion, you've always got to have a driver that will suck up some of your power, and that makes that hard. Whereas one of the advantages of the stellarator is when you've got it going, it should be entirely heated by the fusion. It burns. It's like a fire. It just burns. It just sits there and burns. You shovel in a little more deuterium and tritium, and it burns that too, right? So there are advantages and disadvantages. And I guess I really fluffed your question. So, yeah.
The company you referred to, Heliofusion with Microsoft, what was that again?
Helion.
Oh, and
Helion, they're out of Seattle. They have a concept of colliding plasmas and making a sort of fusion burn drive directly an energy conversion. So if you manage to get fusion to happen really rapidly with a magnetic field around it, it would expand and induce a current directly in a coil. And therefore you can make electricity directly without having to boil water and make a steam turbine. And so they're proposing this. But the truth is that most of the energy in all fusion reactions comes out as the neutrons. So you're throwing away a lot of the energy, even if you can make that work. So I don't know how far they are. They've got a lot of smart people working for them, but they're one of the more secretive companies in that we haven't seen any data from them on anything. And if they really are going to produce electricity by 2028, they must be quite far along.
Do we know if the Chinese are working as aggressively as the West is on this?
Yeah. We know they're working actually more aggressively in their public sector program. They're spending much more money than us. It's estimated that they're training 500 to 600 graduate students in this area per year, right?
Are they ahead of us?
The Chinese program is very derivative of the ITER program, and their technology is very good, but they're not trying too many different ideas. There's a very focused program. But they're ahead on quite a lot of the technology programs. It's a good question. If the conventional approach to fusion works, then the Chinese might be there first. Yeah.
Does your presentation include LENR technology and the DOE and ARPA-E projects that include pilot programs to be on the grid in the next 12 months?
These are low-energy nuclear reactions. No, I don't think that's going to work. I mean, I'll just be blunt with you. That's cold fusion. It's not going to work. And I know ARPA-E has funded a little work in that area. Nobody's ever seen more than a few neutrons come out of those things. In these shots, 10 to the 18 neutrons come out. That's what you need to do if you're going to produce energy.
Go ahead, one more question, please. No, please.
Patents, I take it you and the others have been filing patents, and if so, what's the IP sharing situation amongst you and
If I understood IP sharing, I would be a wealthy man. I mean, this is part of the problem of getting this milestone-based. I mean, we're delayed many, many months in the milestone-based program because the agreement between the DOE and the private companies is very hard to make. Right? DOE wants to, own part of the IP, and the private companies say, well, our investors, and DOE is not paying very much money in this milestone. I mean, these are not big payouts from DOE. And so the private companies are saying, you got to put more on the table. I think if I said any more than that, I would probably get into deep water. So, yeah.
Excellent question, thank you. In a moment, I'm going to ask a colleague to come up and make a presentation, but before I do that, let's thank Steve one more time. Now I'd like to ask Professor Stuart Brown, who's the chair of the Department of Physics and Astronomy, to come up and make a special presentation.
Thank you, Steve. Great lecture. So on behalf of the Department of Physics and Astronomy and the Division of Physical Sciences, it's my pleasure to present to you tonight with UCLA's Moossa J. Arman Award for Innovation in Physics. The colloquium series started in the early 2010s, about 2013 by my count. And since that time, we've had the pleasure of hosting and recognizing scientific leaders in a range of fields, including CERN Council President Eliezer Rabinovici, Stuart Parkin from IBM Almaden Research Center, a pioneer in spintronics and non-volatile memory, Terence Sojowski, the Francis Crick Chair of the Salk Institute for Biological Studies and President of the Neural Information Processing Foundation. And just last year, we hosted a pioneer in the field of observation of exoplanets, Dr. Bruce McIntosh, the director of UC Observatories. So this year, we add your name to that list. There's the award. Congratulations. Thank you so much for coming. Great lecture.
Thank you.
Thank you for coming, everyone. That concludes tonight's lecture.